Hello everybody and welcome to the 9th lecture of MHM 420 780 MUA 782. Last week we talked about boiling. We talked about natural convection boiling, nucleate boiling. We talked about film boiling, transition boiling. We talked about correlations, the majority semi-empirical correlations that you can use to calculate the Q dot boiling. But when we talked about film boiling, we were focused on external film boiling because we have two different film boiling. We have external film boiling and we have internal film boiling. The external film boiling is when the flow is over a heated surface, but the internal one is when it's inside the heated surface. Internal flow boiling we commonly refer to as two-phase flow. It's a little bit complicated for undergrad, or it's postgrad, even very advanced postgrad or even PhD concept, and it's one of the most complicated fields of mechanical engineering. Two-phase flow in a tube shows different flow regimes, as you can see here in this figure, and depends on the relative amounts of the liquid and the vapor phase. This picture in this slide shows the flow development in a vertical tube that is subjected to a constant surface heat flux. So it's based on the constant surface heat flux. Subcooled liquid enters the tube by single phase forced convection. If we go a bit up, the wall temperature exceeds the saturation temperature of liquid and vaporization begins in the subcooled flow boiling regime. This regime is characterized by significant radial temperature gradient with bubbles forming next to the heated wall and subcooled liquid flowing over the center of the tube. The thickness of the bubble region increases further down up the stream, and eventually the core of the liquid reaches the saturation temperature of the fluid. Now bubbles can exist in any radial location and time averaging mass fraction of the vapor in the liquid, and X exceeds 0 at any which X means quality of two-phase flow in a radial location. This is the beginning of saturated flow boiling region. The first stage of saturated flow boiling region corresponds to the bubbly flow. Here, as you can see, bubbly flow region. As the fluid is heated further, the X, when we say X, means that the quality of two-phase flow. So the X average increases and individual bubbles unify to form a slug of vapor. This slug flow regime is followed by an annular flow regime in which the liquid forms a film on the tube wall. So you can see it's annular, it's like a wall. This film moves along the inner surface of the tube while vapor moves at a larger velocity through the core of the tube. Dry spots eventually appear on the inner surface of the tube and grow in size within transition regime. Finally, the entire tube surface is completely dry and all remaining liquid is in the form of droplets that travel at high velocity within the core of the tube in mist regime here. After all droplets when all the droplets are completely vaporized, the fluid consists of superheated vapor, just like superheated vapor here, and the second single phase forced convection region. So start from single phase forced convection, which was based on liquid, and finishes to a single phase forced convection region, but this time based on vapor. And if we want to determine the heat flux in like internal flow boiling without going through the difficult concept of two-phase flow, we can add forced convection and pool boiling heat fluxes together as a rough estimation. So now let's start with talking about condensation heat transfer. Condensation, when the condensation occurs, do you have any idea about it? So basically condensation occurs when the temperature of vapor is decreased to a temperature below its saturation temperature. Okay, so condensation occurs when the temperature of vapor is decreased to a temperature which that temperature is below its saturation temperature. This can be done in two different ways. First one, by bringing the vapor into constant contact with the solid surface that its temperature is lower than that of the saturation temperature of liquid. Condensation can also take place on the free surface of liquid or a gas when the temperature of liquid or gas is below Tsat. In this chapter we are speaking just about the first one, which bringing the vapor into contact with the solid surface that its temperature is lower than that of saturation temperature. Condensation in contact with the solid surface can be categorized into two different forms: film condensation and dropwise condensation. You see the picture here that shows these two different forms. We will talk about them in detail in this lecture and next one. In film condensation, the condensate wets the surface and forms a liquid surface that slides down under the influence of gravity. Okay, so the thickness of the liquid film increases in the film direction. As you can see, the thickness is increasing the direction of the film because of the gravity. Because more vapor condenses on the film, it's like a gravity, and travels down. This is how normally condensation occurs in practice. But in dropwise condensation, the condensed vapor forms droplets, and the surface, instead of continuous film, will be covered by many droplets within different diameters. So you can see different diameters. You have seen it sometimes on the like windows or on the car windows as well. But just give you some ideas that dropwise condensation has much higher condensation heat transfer coefficient. Okay, We are going to talk about it later, but just like keep it as a rough estimation in your mind. But how about the difference between these two? Like, let's say we just, when we look at the picture, so of course we can say easily what's the difference between film condensation and drop-wise condensation. But in film condensation, the liquid wall between solid surface and the vapor serves as a resistance, and this resistance increases when the thickness of liquid film increases. But in drop-wise condensation, droplets slides down when they reach a certain size. There is no liquid film to resist heat transfer, so as I mentioned, heat transfer rates are much higher compared to the film condensation. Why? That's the reason, because the liquid film creates some kind of resistance, but drop-wise we don't have that problem. So it is acceptable to say that the drop-wise condensation is preferred mode of condensation due to lower heat transfer resistance and should be used in design of heat transfer equipments. But many researchers tried for a long time to achieve sustained drop-wise condensation, because it's not important to get it like for a short period of time or once. It's sustained. So they tried different vapor additions, different surface coating, but they were not successful. So it is common to assume that field condensation in the design of the heat exchanger equipment will happen. So let's go then a little bit deeper into film condensation. So if we start with the film condensation on a vertical plate, and this figure shows a typical velocity and temperature profile of the condensate. The velocity is 0 at the wall due to no slip condition, we are familiar with it, and reaches a maximum at the liquid vapor interface. So the temperature, if we look at the temperature of the condensate or temperature profile, is the T sat is at the interface and decreases gradually to Ts at the wall, because if you remember we said that the temperature of the surface is lower than the temperature of the T sat. So from T sat at the here interface goes down to Ts, which is temperature at the surface. This figure shows different flow regimes during the film, because as you can see there are different shapes, so different flow regimes. For condensation on a vertical plate, we can say that we have three distinct regime when the Reynolds is lower than 30, when the Reynolds is between 30 and 1800, and when the Reynolds is higher than or greater than 1800. It's like, let me write it, these three regions. The first region, when Reynolds is lower than 30, we call it laminar or wavy free. The second one, when the Reynolds is between 30 and 1800, we call it wavy laminar. And when the Reynolds is higher than or greater than 1800, we call it turbulent. So let's first let's start with Reynolds number. Why? Because we said that okay, it's based on the Reynolds number. So if you don't find the Reynolds number, you can't really say what kind of condensation you are talking about. Am I right? Because it needs to be based on the Reynolds number. So first let's start with how to find the Reynolds number. In the flow regime, in wavy free, wavy laminar, or turbulent is the same. The way that we find or we can find the Reynolds number is the same. In film condensation, we need just to keep in mind that the hydraulic diameter is for, as you can see here, delta. What is delta here is basically film thickness. So the rest are the same. You know that density, velocity, viscosity, but this like I just wanted, this delta is film thickness. So, and there are some like correlations how to use rho L we use, which is the density of the liquid, viscosity of liquid, average velocity of condensate, all those information. But we are familiar with the concept of HFG and latent heat of vaporization, but condensate in an actual condensation process is cooled further below the saturation temperature. So some average between saturation temperature and surface temperature. Okay, so then we need to define modified latent heat of vaporization. Why? Because, as I mentioned, the actual condensation process is cooled further below the saturation temperature. So since we read this HFG at saturation temperature, is not going to work for us. Why? Because it's not enough. It's plus something else. Why? I just mentioned. We can have the same argument for vapor that enters the condenser as superheated vapor at temperature of TV instead of saturation temperature. So in this case, first vapor temperature should decrease to Tsat, and after that condensation can start. So if we want to be more precise, we can add this section to it as well. So we know that the amount of heat released as a unit mass of superheated vapor at temperature of TV will be cooled to Tsat is CPV. So CPV, this is vapor, CPL, liquid. Okay? So basically it's HFG at saturation temperature, but we have two different things. First, condensation process actual happens at the temperature between saturation temperature and surface temperature, which is lower than saturation temperature, so it's subcooled. We add this section to it. We also mentioned that vapor condenser, like the vapor when enters the condenser, is superheated. Okay, so means that the temperature of vapor, it's higher than saturation temperature, so we add this one as well. Why? Because TV, the temperature of vapor, we said that is higher than saturation temperature. Why? Because it's superheated. In this case was the same. So when the temperature of surface is lower than Tsat, it was, if it's the same, so basically this will be 0 and HFG star will be equal to HFG. That's the reason why we need to use modified latent heat of vaporization when we are talking about film condensation. Now we are going to discuss relations for the average heat transfer coefficient H for the case of laminar film condensation. So very simple one, just laminar. Let's see what we can get. Let's first start with the vertical plate. This picture shows a vertical plate of height L that maintained at a constant temperature of Ts, like a surface temperature, and exposed to vapor at saturation temperature of T sat. We know that because we are talking about condensation, so T surface is lower than T saturation. Since the surface temperature is below the saturation temperature, vapor condenses on the surface. The liquid film flows downward under the influence of gravity. The analytical relationship for the heat transfer coefficient for this case was first developed by Nusselt in 1916. He made some assumption that we are going to use as well, and we want to see if we can find that the correlation as well, or we can't find it. Let's try and see if we can find this correlation. Okay. So as I said, it's a correlation that Nusselt came with, but we want just to see if we can get to the same correlation from this picture and very simple analysis. Okay, so he made some assumption that we are going to do the same assumption. First, plate and vapor are at constant temperature, so there is no temperature variations. Heat transfer across the liquid film is pure conduction, no convection is happening, and velocity of vapor is very low, so there is no drag on the condensate. So with those assumptions, let's try to see if we can find H for this case. Okay, but we also know that the flow is laminar, property of the liquids are constant, and the acceleration of the condensate layer is negligible. So we start with the volume element shown in this figure. So let me just delete this one and write it here. So T is smaller than T sat. So if we start with this volume element in x direction, which is this one, I can say that sigma fx should be 0. Do you agree with me? So f1 should be equal to that. So viscose, what we have is viscose shear force. What else we have? Buoyancy force. So these two should be equal to weight, basically. So that is the sigma fx is equal to 0. Okay, now let's write it down. What is the viscose shear force? Do you remember that? So it's L du dy b dx. Here mentioned. Plus, I said buoyance force, buoyance, so density, gravity, and b dx again. These two plus, they should be equal to weight, which density of liquid, plus b dx. Okay, now let's just write it in the next page and try to see if we can get to the correlation suggested by Nusselt. It's very interesting and nice. Y b dx plus buoyance force is equal to Lg b dx. Okay, so let's say we want to find what is the du with dy. If I put everything aside, it will be mu L b dx, and if I put this the other side, so we have b dx rho L g delta minus y plus rho v g delta minus y. So this will go with this one. So du with dy is equal to g rho L minus rho v delta minus y mu L. So now we have this one. What we need to find a boundary condition. What is our boundary condition? Boundary condition, let's go back to this figure. So boundary condition, can I say that when y is equal to 0, u is 0, no slip condition? And can I say that when y is u is equal to uy? Yeah, so let's implement it. The boundary conditions, we have 2, no slip condition, the surface, the speed is 0, and y is follows the velocity profile. Okay, so if we do the integration and apply the boundary condition, we will have so uy is equal to rho L minus rho v divided by mu L delta minus 2 is y. It's not g, it's y. Okay, so basically first we find out the velocity distribution. Okay, it was very simple. So boundary condition, we have it, and this one we just like do the integration. The mass flow rate of the condensate at the location X where the boundary layer thickness is alpha. So what we want to find the m dot where at the location X where the boundary layer thickness is delta. So if we want to find that one, so m dot x will be equal to a L velocity profile. Do you agree with me? Okay, so y equal to 0 to delta, because it's like the thicknesses L y b d y. You just like put this one y because the a here dy. Okay, so if we do the integration, we have 0 to delta or L. We can just put this from the velocity profile, or L minus v L y delta y22 b dy. Okay, so dy, so all those stuff, these stuff, because there is no y in them, they can come out of the integration, so it will be g b rho L minus rho e divided by mu L 0 to delta y delta minus y22 dy. Okay, so you might say that now is just like a little bit boring, I don't want, but it's very nice when you see at the end that you actually you did exactly the same thing that Nusselt did many years ago. So we reach to this integral. If we want to do the integration, what we are going to have is this one. It will be v rho L, sorry, it's not rho, v rho L here, rho L minus rho v divided by mu L. So we do the integration delta 2 minus y3 x between y0 to delta. So what we are going to have is we are going to have GB rho L minus rho L minus rho E divided by mu L 3.2 minus 3.6 minus 0. So this will be 3.3. If we put it, m dot x will be equal to this correlation, GB L, it looks a little bit like V, sorry, L minus rho V divided by mu L 3.3. Okay, now we found this one. So now how we are going to use it, because it's like it's not very similar to this correlation that we showed from Nusselt. It's like H. Now we have just like we calculated, we find the velocity profile. From velocity profile we found the m dot. Now from m dot we want to find H. Okay, so how we do here, it's very simple. We know that the q dot is equal to hgd m dot, which is equal to kl b dx. You remember what I said? No convection, everything is conduction. So T sat minus T surface divided by thickness of film. So the m dot divided by the x will be KLB HFG T sat minus TS, which is surface temperature divided by thickness of film. So here we find the m dot, so we just like put it in. So d to dx, just like put everything that we had for m dot, e rho L minus rho V divided by mu L 3 is equal to KLB divided by HFE multiplied by Tsat minus Ts divided by thickness. Okay, basically that's it. So not a function of x, 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 not a function of x. All of them can come out, but the thickness is a function of x. So not all, just one of that. We can say that GB rho L minus rho V divided by mu L the 3D delta dx is equal to KLB HFG Tsat minus Ts delta. Okay, so now what we got here, we got to this. So we just need to find this one. So the 3D delta will be equal to, it's just like a x, so it will be just like c. Okay, so it will be like very simply mu L KL T sat minus T surface divided by rho L minus rho V HFG and 1C. Okay, so how about 3d delta 0 to delta? We know that it's 4. Am I right? So delta x is equal to 4 goes on top, so 4 mu L KL T sat minus T S multiplied by x rho L minus rho V HFG to the power of 0.25. Okay, but if you remember here, now we have the thickness. We have the thickness, but the Nusselt was based on h. Okay, so we want to find or calculate the heat transfer coefficient. We know that Q dot x is equal to h T sat minus T surface. We know that. So how we are going to find that one? We also said about the conduction. So Q dot x, if you remember, we said that it's equal to conduction. Finally, we have x is equal to KL delta x. If we apply that one, hx is equal to rho L minus rho V HFG KL to the power of 3 4 mu L T Tsat minus Ts x 14. And after that, H horizontal is equal to 1L 0 to L Hx dx. So it's equal to 0.75. Hx is equal to L, which will be 0.943 rho L minus rho V HFG KL to the power of 3 divided by mu L Tsat minus Ts multiplied by L to the power of 0.4. We advise that in this chapter the thickness of the liquid film at the bottom of the tube can be calculated as well. So now look at this correlation. If we go to this one, it's exactly the same for Reynolds between 0 to 30. So we solved it. So we did exactly the same thing that Nusselt did in 1960. Is it for exam? No, but I just wanted to show you some a little bit of like how from a very simple concept, from the concept of like the sigma forces in x direction should be 0, and after that we just thought about the viscous shear force and buoyancy. We put them together equal to weight, boundary condition, and that's it, and we solve everything with some kind of mathematical manipulation. Is it for exam? No, you don't need to know it, but it's very nice, and I just wanted to share it with you to I think understand it much easier. But it's not for the exam. I just put it for your information. And at the end, if you remember, I said that for in this chapter that we talk, the thickness of the liquid film at the bottom, can be calculated from this. This is H. Let me just write it nice. So you find the H, and after that you can find the thickness of the liquid film at the bottom. Yeah, basically that's it. But a little bit we should know that this correlation that first we find this is the correlation that we find. This will under predict the heat transfer because it does not take the effect of nonlinear temperature profile and the subcooling of the liquid below. So we can modify it by using modified HFG, and finally we can just like add this one to it to sort that problem of under predicting. All properties should be evaluated at film temperature, but HFG and rho V should be at saturation temperature. So now we have the correlation here. It's exactly the same as boiling, but we need to go to the table and read Tsat or Ts. They are numbers, L shape, but how about rho L, rho V, HFG, KL, or viscosity of liquid? As I mentioned, all the properties should be evaluated at film temperature except HFG and rho V. These two, they need to be at saturation temperature. Saturation temperature. The rest should be read from the table at film temperature. What is the film temperature? T is surface, T is saturation divided by 2, the average of it. We said that, okay, it's like this correlation exactly the same as what for basically we found that for Reynolds between 0 to 30, which is the first flow regime that we talked about, is the same as Nusselt that did it for Reynolds between 0 to 30. But let's try to see if we can find another expression as well, because we said that, okay, it's like Reynolds is, let's see, for Reynolds lower than 30. But let's try to find if we can find another like a correlation or explanation for Reynolds based on this concept of condensation. So we said that the Reynolds is equal to for m dot mu b. What is B here is wetted perimeter of the condensate. So if we put that m dot into this correlation, we will have 4 GB rho L minus rho V delta 3 mu to the power of 2 B 3. Why is delta T this one? But from the m dot, we just like, if you go back to the previous one, we just from here, that m dot, just put it here to find it. So basically now the Reynolds will be 4 G rho L minus rho V 3 power of 2. So this B and fit B. So for Reynolds lower than 30, that we said that is wave free flow. In this, rho V is much smaller than rho L, so we can neglect that one. So in that case we will have Reynolds is equal to 4 G rho L to the power of 2 delta 3 mu L to the power of 2. The other thing is, now we have this one, so let's try to apply some boundary as well. So when the X is equal to L, so delta is KL H X equal to L, and vertical, we know that is 43 HAX equal to L. So basically delta X equal to L is equal to KL 34 H vertical. If we add everything into the Reynolds will be equal to 4G rho L to the power of 2 through the power of 2 KL 34 H vertical. So here, as you can see, we can find Reynolds as well. If we put these two into H vertical, because we have the correlation for H vertical, as you can see here, if we add that, finally we will have this correlation for Reynolds. Sorry, for this vertical. So H vertical is 1.47 KL, Reynolds 21.3 G L to the power of 2 divided by 1.7 is for Reynolds between 0 to 30, and when rho V is much smaller than rho L. Okay, so we find another correlation that we are going to use later as well. I'm just like going quickly going to show the correlations that we are going to use in this no, I think it's enough. Let's go back and talk about some correlations and solve one example in the next lecture. Okay, thank you for your attention. Enjoy the rest of your day, and talk to you and continue this topic regarding the condensation in the next lecture.